I'm just going back to what we talked about yesterday. After that, you're going to draw a free body diagram. After this, you'll apply a coordinate system. After that, you'll apply a coordinate system to the problem, and then you'll break up any off-axis forces into components. You'll apply Newton's laws in each direction. At the end, you'll use your newly created relationships to solve your problem. This is what the framework is like. Yesterday, we made it to point 1 and 2, talking about what it is you would be doing. We never got beyond that. So today, we're going to take a look at an example, and we're going to go through all of these parts. So for each one of these, I'm going to try and apply it to a specific example. And we talked a lot yesterday about different kinds of forces and such. The rest of this will come together more quickly. So let's take a look at example 1. Apply a coordinate system and break up off-axis forces into components. Example 1 is already sitting right here for us to take a look at. It is the textbook resting on the table. So, nothing particularly interesting. I have a book and I have the table. Not interested in the table, interested in the book. The book is the object here. So we are interested in analyzing the forces that are acting on the book. So you guys see my book on the table? We're all good? All right. Now, we have to decide whether this is a first law problem or a second law problem. That is our first decision to make. First law or second law. I'll remind you real briefly, this decision is based on what the book is doing or what you think it is doing. Your first choice, a first law problem, means constant velocity or stationary. That's a first law problem. If it's a first law problem, we apply Newton's first law to it, which is the only one we've talked about so far. A second law problem has acceleration, but is also the default. So if you have not been given enough information to know whether your object is accelerating or not, you must choose the second law until you can prove it's a first law problem. Otherwise, you choose based on whether it's accelerating or not accelerating. Be careful. Moving is not a part of that conversation. It's whether it's accelerating or not. It can be moving, it just can't be accelerating. Do you understand? First law problem, correct? The book is stationary relative to the table. So in this problem, I will say it's first law and write quite clearly, net force equals 0. I write at the top of my problem to ensure that I am aware of what the problem is going to be about. All right. After you've done that, we're going to draw a free body diagram. There are a couple of rules ahead of time before we get into the list of forces and drawing a free body diagram. And the first one is to reduce everything with mass to a dot. We are doing single body problems right now. So there's only gonna be one dot on all of ours, but that's only gonna last for a couple of weeks. And then we'll be doing multi-body problems. Be aware, in a multi-body problem, there might be many things involved. 2 blocks being connected together by a piece of string hanging over a pulley. They will say things in the problem like it's a massless pulley or a massless string. That's a sign to you that they don't have mass, you don't include them in the problem. There is no massless pulleys or massless strings. Everything has mass except for photons. What they're really imparting to you is that the mass of that object is so small that it doesn't affect the problem in a meaningful way. Does everybody understand? Because we're going to do labs and we're going to have string and pulleys, and you'll get an idea of massive pulleys, ones that do affect your problem, versus massless pulleys. Massless pulleys are easy to turn and they don't feel like they weigh anything. So it's not like they really exist, it's whether they really impact your problem or not. So keep in mind that, read carefully. Very, very seldom will you have a string that has mass, but not never. The AP exam has had massive string in their problems before. It becomes a dot in your problem to which you have to deal with the force. Now, we have a book, so done. I've drawn my dot to indicate the book. Next, we represent every force as an arrow. And they originate at the dot. So they always start at the dot and are drawn outwards. Next, every arrow must be drawn to scale. This means that you need to pay attention to A, what you've chosen here, whether it's a net force equals 0 problem or a net force equals MA problem. And you have to pay attention to what they say in the question itself. If they tell you that one force is half the size of another, then you better draw that arrow half as long as the other. In the APC exam and in the AP1 exam, they look to see if the arrows are drawn to relative scale. I want exacting standard here. And this also includes direction. If they say the angle is 30 degrees, you have a protractor, you draw it so that it's at 30 degrees. You do everything in your power to make this as realistic a diagram as is possible. Generally, the scale is set by the weight. That's going to be the thing that will set the scale for the whole problem, but not always. If you know the system is balanced, for every left, there had better be a right, and for every up, there had better be a down. You need to show the balance in your diagram. Now, the next part of this is taking this information that we just wrote down and applying it to the list of forces that we have. We have a list of forces already. I gave it to you yesterday. We have the conservative forces, or fundamental forces. I'm not writing them all down. You wrote them down yesterday, right? You have all 3 of them. So you wrote in your notes that there's the gravitational, the electroweak, and the strong nuclear. You put them in your notes from weakest to strongest and from farthest distance to shortest distance. You need to know that. Multiple choice question is going to say, pick which one of these shows the forces in order from weakest to strongest. And it'll have forces in there and stuff, and it's going to have things to throw you off. Like tension will be in that list. But tension is not a conservative force. Now, for our list here, I'm only going to put gravity, because the only conservative force this class worries about is the gravitational force. And we call this the weight. And we will use a capital W to represent the weight. Some forces, but not very many, have an automatic way that you calculate them. Weight is one of those forces. Weight is the product of mass and the acceleration of gravity. So you can write weight or you can write mg. Either one of those is acceptable. Oftentimes, our objects don't have specific masses. It's M1 or M2. So writing M1G and M2G is a good way of differentiating one object from another object when we're dealing with the multi-body problem. But you could also write weight 1 and weight 2. I would just make sure you coordinate that, because sometimes it's lowercase m and capital M. And boy, those look the same when you're drawing them, right? Especially if they're on opposite parts of a diagram. Be aware and cognizant that that's the way they will do things on the AP exam and the way I will do things on our test too. Next, we have contact forces. And I only talked about 2 yesterday, although there are others. Contact forces require, you guessed it, contact. Something has to be touching the object. And there are 2 I talked about yesterday, the normal force and the tension forces. Normal forces are pushing forces. And I'll represent those with the capital N. Tension forces are pulling forces. And I'll represent those with the capital T. You can have multiple surfaces touching an object, and you can have multiple ropes attached to an object. So there can be more than one normal and more than one tension. So be careful. The thing you need to know though, normal forces are perpendicular to the surface. There we go. They're back. Normal forces are perpendicular to the surface. Tension forces, that always depends on the cable or the string or whatever. Those dictate the direction. All right, so we have conservative forces, contact forces, and lastly, resistive forces. That's friction and air resistance or drag. Since I know you guys can't see the bottom of the board, I will represent friction with a lowercase f. There are multiple kinds of friction. There's friction for 2 surfaces that are sliding and friction when an object's at rest. But in all versions of friction, friction resists one surface from sliding past another. I'm not going to write that in there. You should write it into yours. Resistance is a force that tries to prevent one surface from sliding past another. Resistance is a force that tries to prevent one surface from sliding past another. Although I think this should be obvious, it never is. So let's understand, friction has to be parallel to the surface. Right? If we're trying to prevent one surface from sliding past the other, it has to be directed along that surface. And it also has to be directed in the opposite direction of motion. So if your object is sliding to the left, friction has to be to the right. It's trying to prevent it from sliding. I know these things sound obvious, but students do weird stuff. And I'm giving you information you should put in your notes. Trust me, you've never done this before. Friction has to be parallel to the surface and has to try and prevent one surface from sliding past the other. So it will be in the opposite direction of motion. Not acceleration, opposite direction of motion. And I think this is obvious too, but no one ever connects these dots. Every normal force could have a frictional force with it. Normal force is contact with a surface. Friction is a force directed along a surface. If there's no normal force, there'll be no frictional force. But if there's a normal force, you should always consider if there's friction. Luckily with drag, you only have to worry about air resistance or drag if they tell you it's in the problem. If they don't bring it up, it's not there. Well, I made a mess of that, so you're not going to get them up there. Hopefully they're in your notes, because I made a mess of them and I can't bring them back. So let's go to this problem here. I'll go through the list. I will say the list out loud, but I messed up the list, so I can't bring them back for you to see it. All in service of making sure the people in the back could write down friction and air drag. So here we go. Book, resting on table. Start at the top. Is there any conservative force acting on the book? The answer is always going to be yes. Get that one right. Be the first person to say it so you sound like you're smart. So there's always going to be weight in every problem that we do here. So start by drawing the weight in. It should be a force directed downwards from the object. Remember, every force is an arrow directed in the direction of that force, beginning at the dot and directed in its direction. And every one of these arrows should be labeled with the force. When it's weight, you can put weight or mg, that's fine. Moving on to contact forces. Is the book in contact with a surface? The table. So there must be a normal force acting on the book. That force must be directed perpendicular to the table. I'm pretty sure we can all agree the table is level, so perpendicular to the table will be a force directed upwards. My rule about drawing these forces is to try and indicate them and draw them to scale. So I want to draw an upward force that I think is balancing the weight. I'm pretty sure the table is supporting the book. And I know from the beginning that I said net force should be equal to 0, so I'm trying to make my weight commensurate with the idea, trying to make my normal force the same size as my weight. Label it N for normal force. Any cables, pulleys, strings attached to the book? If not, there's no tension. Is the book being held in place by friction? Now that's a more difficult question. If my table is level, there's no need for friction to hold it in place because there's no reason for it to slide across the table. So in this instance, I'm not sure if there's a frictional force. Now, keep in mind, I know what you're thinking. Maybe there is friction. Maybe friction's holding it in place, but what would that make you do? What direction would you draw it if it's holding it in place? Friction only exists to try and prevent it from moving. Do you think the book is trying to slide right now? If not, there's no reason to draw friction. I think we're done. I think we've identified all of the forces acting on the book. Because we're done, we're going to move on to the next step, which is to study our free body diagram. Now, in practice, this is a free body diagram. On a test, if it says to draw a free body diagram, you stop here. You don't have to do anything else. But you may need to draw on your free body diagram to actually solve the question. You might need to resolve things into components, which means drawing in triangles and stuff like that. Do that separate on a test. In your homework, do it right on your diagram. But on a test, if you have to draw a free body diagram, they'll say, here is a dot, draw in a free body diagram, and it will say very clearly, do not draw in any components or anything that aids you in solving the problem. It'll say it in the test to just leave it like this. But if you have to do work on this, do it elsewhere on a test. Everybody following what I'm trying to say? All right. So this is where we start adding to our diagram, and the first thing is to draw a coordinate system. You have two priorities. Priority 1, on drawing a coordinate system in. Draw in a coordinate system. How did I phrase? And break up off axis forces into just gonna get comp. A coordinate system is exactly what it sounds like, X and Y. You must draw the X direction and the Y direction perpendicular to each other. I know that sounds so stupid, but I see every year students who draw the X in a way that they want and the Y in some other weird way because it's convenient. But if you choose to make the X direction like this, you must make the Y direction perpendicular to it. I don't think this is a particularly good coordinate system. Not for this problem. However, there are two priorities you should live by. And these are priorities. You do one first. If you can't do one, you do number 2. Sounds like going to the bathroom. Priority number 1. That is your first priority. You align the positive direction with the acceleration. It will be impossible for you to solve the problem if you do it otherwise. So always align the positive direction with the acceleration. Priority number 2. Well, in priority number 2, if you don't have to worry about priority number 1, then you get more opportunity to choose how to draw your coordinate system. So align it with the most number of forces. For every force that it's not aligned with, you have to do trig. So you want to align it with the most number of forces. I mean, we only have 2 here, and they are already in one dimension. This is not a particularly good example of what it looks like to make a decision about priority number 2. But you want to do your best to try and align it with the most number of forces to reduce how much work you have to do. The more forces you have to do trig on, the more complicated your problem is going to be. Go ahead. Align the coordinate system. Yeah. So I'm going to put the X this way. And I'm going to put the Y this way. Right? I'm aligning it with all of the forces. Go the extra mile. Tell yourself what is positive. Tell yourself what is negative. Be very clear. Now, once you've drawn in your coordinate system, if there are any forces that are off axis, you have to resolve them into components. An off axis force will look like this, right? It'll be off the axes. It won't be lined up. And you will have to break it up into a component this way and a component that way. One that lines up with the X and one that lines up with the Y, which means you'll be doing your trig on all of those. So you want to try and reduce how many times you have to do that. So try and be careful about your coordinate system. When all of that is over with, your last step is to apply Newton's laws. Whatever one you chose at the very beginning. However, you can only apply this law in each dimension. You can only do one-dimensional math. So you're going to be applying the law in the X direction, and you'll be applying the law in the Y dimension. You're applying a law. This is not a formula. It's not an equation. It's a set of instructions. I talked about these instructions yesterday. I want to reiterate them today. This means to add up. So as an instruction, get rid of the 2. Add up. It's telling you what to do. Add up all of the forces. That little bar means take into account their direction. This means positive and negative, right? For us, direction is positive and negative. And lastly, set them equal to 0. Newton's second law will say something else, but Newton's first law says to add up all the forces, taking into account the direction, and set them equal to 0. We have 2 forces here. We have none in the X direction, so I don't even have to worry about the X direction. But I have 2 in the Y direction, so I'm going to add up all the forces in the Y direction. There's 1 pointed upwards and 1 pointed downwards. So positive N minus W equals 0. I'm just following the instructions. That's all you do. When you have completed this, you will have created a couple of these. One for the X direction and one for the Y direction. This is the end of applying the force concept model. But it's at this moment that you will have a couple of equations that you created that custom fit your problem. So whatever your problem is asking about, these equations will help you solve it. The force concept model is an analysis of a system. It allows you to analyze the problem and come up with equations that could be used to solve your problem. I'm being very careful about the way I say this, because every single problem means a new set of relationships that you'll create on the site for whatever your setup is. Example number 2. I have done one. I am not doing them any longer. You will have to do them and show me your work. So, seeing some interesting choices out there, and I am seeing kind of what I expected. Not all of you. I did see a lot of good stuff, but I also saw a lot of not so great. So let's go through, and by the way, this is as much time as this should take. So I gave a little bit more, but it should only take you a few moments to put this together. So let's start at the beginning. Is there a conservative force acting on the calculator? Sure. I would always start here. It's the way to go. So I've drawn a downwards arrow to indicate the weight of the calculator. Is the calculator connected to, I should have said this from the beginning. Is this a first law problem or a second law problem? First, the calculator was stationary relative to the book. There. So we drew the weight in. Is the calculator in contact with the surface? Yes. Now, a lot of you just drew an upwards arrow again. But the definition of the normal force, the word normal means perpendicular, just like back in geometry. So this should be an arrow drawn perpendicular to the surface. So this has to be an arrow that is this way, right? Perpendicular to the surface. Not up. Don't copy your last one. So I need to draw an arrow that is perpendicular to the surface. And in drawing this arrow, I need to be careful to consider how long should I draw it. It's clearly lifting or keeping the book in place or pushing upwards on the book. The calculator's not falling through the book. But also when I look at this, I don't think that this is balanced. For every up and down, for every left or right, this looks unbalanced to me. There's probably other forces acting on the system. Is there any rope, cable, string attached to the calculator? There's no tension. Do we think there is a resistive force that is preventing the calculator from sliding? Now, if there is friction, there are rules. Friction has to be drawn so that it is parallel to the surface, which must make it perpendicular to the normal force. That means that when I draw the frictional force in, it will be parallel to the surface and perpendicular to the normal force. I'm doing everything I can to make this perpendicular. You have a protractor. You can make sure it's perpendicular. Label it friction. Every left, a right, every up, some down. That's it. This is a free body diagram that could be used to solve our problem. We now have to add to this a coordinate system. Is our system accelerating? Because there's no acceleration, we can choose a coordinate system that is aligned with as many forces as possible. We can align this coordinate system however we choose. I could decide to align it with the weight. I think this is a bad choice though. If I align it with the weight, then I don't have to break the weight up into components because it's already lined up with the negative y direction. But I will have to break up the frictional force and the normal force into components. This seems like a poor choice. I think a better choice will be to line it up with the normal force. If I line up with the normal force, the friction is perpendicular to the normal force. So I know that lining up with the normal force means I'm lining it up with the frictional force. So make this the positive x direction, this the positive y direction, and only one of my forces now has to be resolved into components. And that's where the trig comes in. There'll be a portion of the weight in the x direction and a portion of the weight in the y direction. You'll do trig, and then you'll be able to do net force in the x direction equals 0, net force in the y direction equals 0. I see the likelihood that there is a weight in the y direction and a weight in the x direction. That's going to be trig. Since I've chosen positive and negative, then in the x direction, I will have friction, positive, minus weight in the x direction equals 0. I'm not doing the trig right now. But I also have in the y direction, normal, which is positive, minus weight in the y direction equals 0. But there's trig. I could do the trig too, right? This is the opposite side. This is the adjacent side. You see the trig in here. And you see why we did the north, south, east, west stuff? It's in preparation for this. All right, next example. Example 3. With example 3, I'm going to introduce another force. And this one is going to feel a little bit weird, but trust me when I say it's not a big deal. Sometimes a force is just given to you as part of the problem, and you have to roll with it. We're going to call these applied forces, in that they say in the problem, a force is applied to an object. Just do whatever it says from that point forward. Ready? Force is applied to the book, and the book slides up the wall at a constant velocity. Okay? Everybody follow along with it? A force is applied to the book, and the book slides up the wall at a constant velocity. I'm willing to draw a bit of a picture for this one to help you out before you get started, so you understand what I mean by an applied force. There was the book, but then there was me pushing on the book. I am the applied force. If you have an applied force, just label it FA for applied force. It's truthfully a contact force. And they're going to give you information about it, an angle or something. I was the applied force. Because of me, the book slid up the wall at a constant velocity. Draw a free body diagram that could be used to solve this problem. Is there a conservative force acting on the object? Yeah. This one's easy. Oops, don't want to draw that. Be the first one to say it. Jump on it right away. So yeah, I'm draw an arrow downwards. I'm going to label it weight. There was a force given to me, an applied force. When you go to draw that, follow the rules of forces. Forces are always drawn from the dot and drawn away from the dot in the direction of the force. So when I go to draw this one, it should be drawn from the center of the object, going away. Don't draw it towards the object. So here I'm going to draw a force like that. That's drawn away from the object. I'm not going to draw theta in because I don't yet know what my coordinate system is going to be. Next, is the object in contact with any surface? In contact with the wall. So I need to draw a normal force that is perpendicular to the wall. Right? I'm just following the rules, right? The rules are very explicit. So all of you drawing right now, the rule told you everything you had to do. If your instructions are not clear enough, you need to clarify them, because none of this is taking very long. And I'm not being mean, I'm not being cruel. I'm saying you need to buck up, you need to step up and rise to this challenge. You can do it. Now, is there any cable, string, rope connected to the book? No. Move on to resistive forces. Is there a force that is acting to prevent the book from sliding across a surface? Probably, yeah. I think there's probably friction in this problem. Friction has to be parallel to the wall, which means I'm either drawing it upwards or drawing it downwards. It's trying to prevent the book from going upwards. So I'm pretty sure I should draw the friction downwards. I don't think the frictional force is pulling the book up the wall. I think it's preventing me from having the book go up the wall. There are two ways you can draw this force. You can draw them side by side like I've done here. That's what I prefer. But it is also allowed of you to draw the friction like here and stack the forces. There's advantages and disadvantages to each. I like them being drawn all from the dot outwards. AP accepts both of these. So I'm going to continue to do it the way I like. Consider a coordinate system. Is my system accelerating? Is my object accelerating? Or is it moving at a constant velocity? I said constant velocity, so we accept that as fact, constant velocity, which means I don't have to do priority 1. I can do priority 2 to align my coordinate system with the most number of forces. And I think all of you would agree I want to do it this way, so only the one force has to be resolved in the components. We good? I have a wall and a roof line. I want to hang a sign so that people walking along the wall can see the name of my store. I'm going to hold it with a cable going right to the wall and another cable going to the roof. The cable makes an angle of theta with the roof. Can you draw a free body diagram for the forces acting on the sign? There's only 1 minute left in class. You will not finish this. But rest assured, I'm going to be posting practice for you. Please practice by Monday. We want to be experts by Tuesday. You'll notice we haven't started the actual work here. We're just drawing pictures, right? But ask anybody who's an AP1, if the picture's wrong, you can't do anything. The picture has to be spot on. So we're going to practice until we get it spot on. First quiz on this is Tuesday, and we'll have one every day until we get it perfect, right? Yeah. Yeah, I'm just trying to hang a sign. I'm going to use 2 cables to do so. One that's connected and it's horizontal, goes right to the wall, and one that's hung at that angle, and it's to keep the sign in place. Bye, folks. Have a good week.